I was at a party recently and a friend asked me whether there was a formula to calculate the radius of a circle if you had an arc and a chord joining the ends of the arc. And I said, I think there is maths. I've seen maths around that sort of stuff, but I'm not familiar with it. The next day I'm on Google and I discover two quite extraordinary things. First of all, there is a formula. But second, you can't solve it algebraically. You use a method of iteration. And the method most commonly used was devised by none other than Sir Isaac Newton. Suppose we have an arc and we're going to say that it's 14 units long. And suppose the chord joining the ends of that arc is 12 units long. Well, the radius is of course going to be designated by r, and theta will be the angle in radians that's subtended by the arc at the center of the circle. First of all, we know that the length of the arc is given to us by A equals r times theta. And the other thing that we know is we've got this right angle triangle here. Well, we can see that sine of theta over 2 is going to be c over 2 divided by r, which is to say c over 2r. What happens if we make r the subject of the first equation? Well, that's going to give us r equals a divided by theta. And if we substitute this into the second equation, we have sine of theta over 2 equals c theta divided by 2a. Well, we know c and we know a. And if you can solve this equation for theta, you can substitute it back into the first equation and you can find r. Unfortunately, you can't solve this using algebra. The way to do it most commonly is to use what's known as the Newton method, sometimes known as the Newton-Raphson method, and it uses iteration. You could do it in Excel, you could program it. I happen to do it in Google Sheets. To use the Newton method, you start by writing a differentiable function and you set it to 0. So we're going to have f of theta equals 0. We can do this by moving the sine part of this equation to the right-hand side of the equation, and that gives us f of theta equals c theta over 2a minus sine of theta on 2, and that of course all equals 0. Well, now we need to seed this function with an approximate value for theta. In our case, I'm going to start with an example of theta being 2 radians. Next, we iterate a second, hopefully more accurate solution using the Newton method, and here's the Newton method. It says that theta 2 is going to be theta 1 minus f of theta 1 divided by f dash of theta 1. Well, if we recall that f of theta is c theta over 2a minus sine of theta over 2, it follows that f dash of theta is going to be c over 2a minus a half cosine of theta over 2. So here's the expression for theta 2, and of course this would be theta 3. You can see the general form there. If, as I say, we start by estimating theta at 2 radians, we get the following results. f of 2, because theta is 2, is going to be 12 times 2 divided by 2 times 14, minus sine of 2 on 2. That's going to be 0.01567187233. Remember, we want this function to be as close as possible to 0, and then we iterate it and hopefully get even closer. At 0.01567, we're already very close to 0, which is nice. Now consider f dash of 2. Well, f dash of 2 is going to be 12 divided by 2 times 14, minus a half cosine of 2 on 2, and that's 0.158, etc. And so for theta 2, which is our first iteration of theta, we're going to have theta 2 equals 2, which is theta 1, minus 0.01567, etc., divided by 0.1584, etc., and that gives us 1.901 and a little bit more. Now what's pleasing about that number is it's quite close to our first estimate of theta equals 2, and that's a good thing because it seems to indicate that we're probably in the ballpark. What can happen is if you pick a value that's wildly out, the Newton method will actually not converge, or it will, but to an answer that isn't correct. So in our case, that seems like that's not happening. Let's continue. This time we start with theta equals 1.901, etc. And we get f of theta equals 0.00101825901. Now that's 15 times closer to 0 than our first f of theta. And that's a really good indication. F dash of theta is going to be 0.1379 and a bit more, and if we plug all those numbers in, we get our next value of theta is 1.8936, etc., which is now less than 1/100th of 1 radian smaller than our first iterations. So we know we're awfully close to a solution. If we do one more iteration, we get theta equals 1.893652 and a bit more. On the fourth iteration, Google Sheets just gave up and straight up set f of theta equal to 0. and it locked theta in at 1.893652.041, and R equals 7.3931217001 after just 4 iterations. You have to love Isaac Newton.